A sealed habitat is never just a strong shell. The surprise is that the shell often is not the main risk. The real frontier is long-duration integrity across sensors, seals, access, and the hazards created inside. Start with the basic split in failure logic. Structures that face pressure from the outside, like submarine hulls and deep-sea pods, usually fail by buckling. They can collapse from instability before the material ever breaks in a classic strength sense. Small imperfections matter, like being slightly out of round, a weld that shrank unevenly, or a dent that looks cosmetic. In practice, geometry control, stiffener layout, weld quality, and collapse margin dominate the safety case. Now flip the pressure direction. Internal pressure habitats and containments fail through stored energy, leakage paths, and the behavior of penetrations. Hatches, windows, valves, cable glands, and feed-throughs are not accessories. Each one is a candidate leak path and also a stress concentration. Even if the vessel wall is thick, the system can still be fragile at the interfaces. Here is the second counterintuitive finding. A sealed container can become dangerous even when the outside world is calm. Internal pressure can grow after closure because the contents change. Chemical reactions can generate gas. Radiation can generate gas. Heat can vaporize liquids or expand headspace. A fire inside a sealed volume turns the problem into a rapid pressure rise event, even if nobody thought they were building a pressure vessel. The containment may be strong, yet still exceed its certified bounds due to internal overpressure. That leads to a third finding that strategy leaders often undervalue. Instrumentation under seal is not optional, and it is not easy. The safest sealed systems are the ones you can monitor without opening. Pressure, temperature, humidity, atmosphere composition, liquid level, structural strain, and leak state all need to be sensed through a boundary that you are trying not to penetrate. If you cannot measure state under seal, you cannot run long-duration sealed operations with confidence. Monitoring alone is not enough, because sensors drift. Calibration becomes part of the architecture. Replacement becomes part of the architecture. Data integrity becomes part of the architecture. If a sensor is the only way you know pressure is rising, but you cannot trust it, you do not have a safety system. You have a dashboard. The fourth finding is that access is its own subsystem, not a hatch detail. Moving people, samples, cargo, tools, and waste across a sealed boundary creates risk every single time. You can lose pressure, you can mix atmospheres, you can transfer contamination, you can damage seals through wear. Crossing the boundary is an engineered procedure with hardware, interlocks, and cycle limits, not a casual operational act. Cycle count becomes a life-limiting variable. Every opening and closing is a load event on seals and alignment features. Over time, operational tempo can erase the margin you thought you had at commissioning. How often do we use it has to be treated like how much pressure do we carry. Next is a framing that helps unify design reviews. In sealed systems, there are several boundaries, and they do not perfectly overlap. The pressure boundary holds the pressure differential, using shells, joints, gaskets, hatches, windows, penetrations, valves, and relief devices. The containment boundary prevents transfer of hazardous material, vapors, aerosols, organisms, or radiation-bearing matter. The habitability boundary keeps temperature, humidity, atmosphere, contamination, noise, and human access within limits. Then there is the certification boundary, the narrow envelope of assumptions and test conditions under which the system is declared acceptable. A structure may survive beyond that envelope, but you are not allowed to rely on it. From a capital allocation perspective, the biggest near-term gains are not a miracle material. They come from integrated sensing, better modeling, and better lifecycle governance. Analysis keeps improving, but even perfect models will overstate stability if fabrication imperfections dominate collapse margins. Certification has to specify acceptable imperfection limits, not just nominal geometry. So what should leaders do with this? Fund sealed volume monitoring before expanding sealed operations. Require internal overpressure scenarios as first-class hazards, including gas generation and fire-driven pressure rise. Treat access architecture as a design requirement, with cycle tracking, maintenance intervals, and degraded procedures. Mandate machine-legible lifecycle records covering geometry, materials, welds, penetrations, proof tests, pressure cycles, hatch events, sensor history, repairs, and relief device maintenance. If a sealed asset cannot export its state history, it cannot be managed at fleet scale. The memorable line is simple. In sealed worlds, the boundary is not a wall.